Right, I guess we are starting. Hello, thank you for coming to my talk, Ruby and the World Record of Pi Calculation. My name is Haruka Iwao, and I'm a software engineer / SRE at Google Cloud in Seattle. So why am I here talking about Pi and Ruby? Well, I'm a twice world record holder of the most accurate Pi ever calculated with 31.4 trillion decimals in 2019 and 100 trillion decimals in 2022. So I know a little bit about Pi and Pi calculations. And before talking how, let me talk about why we do this. Like, why do we need more digital Pi? Because we only need 30, 40 decimals for most scientific computations. As Donald E. Knuth says in his The Art of Computer Programming, human progress in calculation has traditionally been measured by the number of decimal digital Pi. So by calculating more digits, we are somehow showing that human civilization has been advancing and we are basically getting better at math. So I'm preparing for a potential extraterrestrial intelligence invasion or something. And in fact, we've been doing this for thousands of years. The earliest known Pi records were around 2000 BC. So it's basically 4,000 years ago. And since we got modern computers, the number of digits have exploded. This is a logarithmic graph. So it's more than exponential. It's an exponential growth. And Pi is also a popular PC benchmark. In 1995, SuperPi was released by researchers at the University of Tokyo, and it can calculate up to 16 million digits. And then 2 years later, Pi Fast was released, and it supports up to 16 billion digits. And in 2009, Y-Cruncher was released, and today it supports up to 108 quadrillion digits, although nobody has tested that. And there's another category, and Pi is also a popular benchmark for PC overclockers. They calculate way fewer digits, like 1 billion digits, really fast. And the current world record is 4 seconds and 408 milliseconds. And the second place is 4 seconds and 442 milliseconds. So they are competing by the milliseconds. It's fairly competitive. But today, the calculation is about massive trillions of digits of computations. And we need to work within certain constraints, like resources or environments we have. And let me go over each step. So we are using Y-Cruncher. It's developed by Alexander E. And he started the project as his high school project. And he's been working on it for a few decades. And it's currently the fastest available known program to calculate Pi on a single node computer. And single node computers here mean just a non-supercomputer. And it's written in C++ and optimized for modern CPUs. And it supports some of the latest instructions like AVX512. And to calculate trillions of digits of Pi, you need a fairly fast computer with a lot of memory and storage. And for 100 trillion digits, you need 468 TB of storage or memory or work area. And we don't have that much DRAM, unfortunately. You can't fit everything in DRAM. So you need to attach storage as a workspace. And the storage system is usually orders of magnitude slower than the CPU. So in other words, CPU speed isn't very important. The important part is the I/O and disk throughput. And the 100 trillion calculation took 157 days. And the calculation moved 62 PB of data. And the average CPU utilization during the calculation is just 35%. So basically, 2/3 of the time was spent on I/O and waiting for the disk to feed data. So with infinitely fast CPU, the calculations still take more than 100 days. So you know how important the storage is. Now we have some moving pieces. We are using Google Compute Engine as the environment because I happen to work for the cloud provider and I had access to the resources. And the maximum disk size you can attach to a single VM is 257 TB bytes. It's fairly big, but not enough for our case. We need more than 500 TB bytes, including some buffers, because we can't precisely measure the exact disk requirement. So you need to mount the additional disk somehow using OS features. And in our case, we use RubyKaigi, which is an industry standard protocol to mount block devices over TCP/IP, and it's implemented in the Linux operating system. And if you use network, the network bandwidth limit is 100 gigabits per second. So that's the throughput we want to maximize. And the overall architecture will look like this. We have the main VM running Y cruncher. This has some beefy CPU, and there are additional storage nodes providing RubyKaigi targets, and they provide workspace needed for Y cruncher. And in the top right corner, we have a small 50 terabyte disks attached directly to the Y cruncher VM, but these are used for the final results. They are not used during the calculation. So we want to maximize the throughput between the big box in the top, like at the top, and the array of the storage nodes. And if you look closer inside the paths of data, there are multiple layers involving, especially when you use some kind of network-attached storage. So Y cruncher writes to the file system, and then the file system issues IO request to the Linux or kernel. And there is this IO scheduler reorders and dispatches IO requests. And then the request would go to the RubyKaigi initiator, the client. And then the packets will travel through the TCP/IP kernel stack. And then the data will travel over the cloud network, which we don't have much control over. And then it goes reverse from the bottom TCP/IP, RubyKaigi target, and the IO scheduler to the storage. We don't have a file system here because it's a block storage. But there are a lot of layers and parameters you can configure. For example, for the file system, do we want to use ext4, XFS, or something else? Do we want to use an IO scheduler, like the deadline scheduler, or nothing? There are TCP/IP parameters that affect performance, like the buffer size or the congestion algorithm. There are some RubyKaigi parameters, like queue depth and the number of outstanding requests you allow. And do we want to allow simultaneous multi-threading for the CPU, or just one thread per core? And Y cruncher has a very important parameter called bytes per stick. This is basically a block access size. And there are cloud-specific configurations like instance type or persistent disk type. For example, do we want to use an SSD disk or some balanced disk or some more throughput-oriented disk? So there are a lot of parameters, and you want to make sure that you're choosing the best parameters possible. Because every tuning goes a long way if the calculation is massive. The calculation took multiple months, which means if something is 1% faster, it could save a day in the total computation time. So Y cruncher has benchmark mode, and you can try some different parameters. But each run takes about 30 to 60 minutes. So you definitely don't want to wait in front of the terminal and then change the configuration and try again. You might want to automate some parts. So let's talk about the automation. Automating most of the things, but not all, importantly. This is what the Y cruncher's config file looks like. It looks like JSON, but it is not. It is not YAML. It's a custom format. So you can't use any of the standard libraries to manipulate the file. There's so much love and hate towards YAML or JSON, but you appreciate the standard libraries available. So how do we deal with that? Here comes ERB to the rescue. So if you use Ruby, we probably use ERB as well. ERB is a template engine. You put a Ruby code in the bracket block, and that runs as Ruby code. And if you add the equal sign, then that replaces the block as the output of the code. And for example, if you put the string reader in the block, the output would include the string reader. And there is actually an ERB talk happening right now in the main hall. But thank you for coming to my talk. I'm sure you can check the recording later. There are two ways to use ERB. For example, if you have that file in the top right corner, you can pass the location as the command line parameter to the ERB command and get the output. Or alternatively, you can use the ERB class from your code, and basically you read a file, pass the file content to the ERB class, and create the object and print the result. These two methods basically yield the same result. So I made this custom script. It has some parameters, like bytes per sec, and number of disks you want to attach to the virtual machine. And then you get the bench template config ERB file, and then set the parameters, and write the config file, and then call the system method to launch Y cruncher. So instead of writing a separate shell script, I decided to do pretty much everything in the Ruby script. And this is like about 10 lines. This fairly small Ruby script runs Y cruncher with different number of disks, like 32, 34, 36, all the way to 72, and it's automatic. So if you start this script when you leave the office, and the next morning, hopefully you have the final result ready for you. And this is the ERB file. And this is just a portion of the overall config file. But you need to set each storage volume as a lane in lane in Y cruncher. So you can write loops in ERB, and here you just need to define one lane template, and then that expands to multiple lanes. So Y cruncher recognizes and uses these all different disks. And you might ask why ERB are not your favorite template engine, because I'm a Rubyist, I think. And any tool could have worked, in fact. But I picked something I'm already familiar with, because the goal is to finish benchmarking as quickly as possible and not about learning a new tool. So this is my comfortable path. And if you run Y cruncher in the terminal, this is what the result will look like. It's color-coded, really nice. And you see, if you run the program, you can actually see the progress animated, and you can see the result. The most important numbers are down here: writes, reads, throughput, and some Y cruncher specific parameters. So we somehow need to extract these numbers from this output. We save the result to the text file. So let's take a look at the text file. And the less command warns me of a binary file. This is weird. Why is that? Because it looks pretty. So if you open the file, it contains a lot of escape sequences to make the output pretty. And I don't know of any options to disable the escape sequence. So you need to work with this and somehow pull the data you want. And this is the final result. So I wrote this shell one-liner to extract numbers, but let me explain step by step why I ended up with this one. All right, first we need to get the lines we need, because the overall output is fairly big, so we don't need everything. We just need the lines we care. So the first regular expression is fairly simple. We pick some string keywords like file memory, sequential, threshold, computation, disk I/O, and then get these lines. There are still extra lines, but we don't need too much. We don't need to worry too much about the extra lines here, because we will process the text file further. This still contains the escape sequence. So let's fill the lines. So as you see the result, you see the gigabyte per second for the all important numbers. So I decided to use that as a marker and extracted the numbers with another regular expression. And you could write a single grep regular expression to extract all these numbers, but I think splitting it into two separate commands is easier to understand and also debug. And if you look at the result, some lines appear twice, because YCruncher apparently writes the final result on a separate line for some of the results, but not all. So you have the first 4 numbers repeat, and the last 2 numbers, the computation and this guy, or the last 2 lines, only appear once. So we need to extract these lines. How do we do that? Can we write a regular expression here? You could, but there's another command called sed. You can use any command, but and often you probably use sed to replace text in a text file. But you can also use sed to extract lines. Sed has this n option to output only matching patterns. And then if you just put a number as a sed command, that specifies the line count. And then you put the p command instead to print the current matching pattern space. So if you put 2p, 4p, 6p, 8p, 9p, and 10p separated by the semicolons, then it basically tells sed to print lines 2, 4, 6, 8, 9, and 10. So you get the result. Of course, you can do this in Ruby, but this is the way I decided to do. Now, we don't need the gigabyte per second as markers. I just kept it because it's easy to tell if something goes wrong. But we can remove them. So just another grep to just put the numbers. Now, when you have a lot of data, you want to use a CSV or TSV or some kind of structured file, although some argue CSV is not really structured, to process those numbers. So in this case, we have separate numbers on separate lines. So we want to convert them into a comma-separate line. How do we do that? You can use, of course, Ruby, or probably sed, anything. But there is a specific command in the Linux toolkit that does that. There is a command called paste. I think this is more less known command for Linux users. It reads the file from the input and then replaces the new lines with the delimiter of your choice. So if you pass a comma as the delimiter, then it puts all the lines in one line separated by the comma. So it doesn't obviously work for all cases, but in this case, this is good enough. So done. We have a CSV file record. And then the benchmark results spread across multiple files. So you just need to use the find command to get all the results. And then you have a CSV file in the terminal. Now, we have the CSV output and want to do crunch some numbers. What's the best tool? Well, there is Jupyter. Well, there's also a thing called Google Spreadsheet or Google Sheets. And I use this because this is fairly popular at my employer. And this is the actual spreadsheet when I was doing the benchmark. I put some columns for parameters that I was planning in the first place, but I ended up with extra parameters that I wanted to try, so I added a small notes section in the last column and decided to add random like notes there. This is not organized or structured by any means, but this is just enough when you have a fresh memory while you are working on it. And there's another spreadsheet. This shows the throughput for different numbers of disks. So I got a confirmation that YCruncher scales fairly well up to 72 storage volumes. And the difference between the first config and the best config is pretty big. The most important number is the BSD IO. And this is the Y-cruncher specific workload simulation by the benchmark mode. And it's more than 200% faster. So if the overall calculation took 157 days, if I just try the first configuration, the calculation could have taken more than 300 days. So by doing some benchmark, I saved more than 5 months and a lot of companies' money. And at this point, you're wondering, hey, I'm at RubyKaigi, why are you talking about Linux commands? Well, I'm more familiar with Linux commands for text processing. Of course, you can write everything in Ruby if you're more competent. I'm not very competent with Ruby, unfortunately, but I'm here. And also, when I'm dealing with some unknown input format, I find the command line style is easier to try different regular expressions and parameters. So that's my style. And it's also a one-off trial. You don't calculate pi regularly every month for like 5 years. It's not a production system, so you don't have any maintenance concerns. And if Y-cruncher changes the format in the future, your program might break at some point, so there's no point optimizing further. And Google Sheets is easy to share and collaborate with, especially with my coworkers. So that's the tool of choice. And again, I didn't want to lose more time benchmarking versus improvements. So if I spend 1 month trying to figure out something and only saving 2 weeks in the final calculation, it doesn't make a lot of sense. So that's the trade-off. And with the final configuration, I run the program, and a few months later, I got the final result. And so this is what you'd see in the screen when Y-cruncher finishes the calculation. And now, before we wrap up the conversation, I want to talk about a Ruby story, my story, to the world records, because this is RubyKaigi, and I think some story about a Rubyist would be interesting. My first RubyKaigi was in 2009 in Tokyo when I was still a student in university, and I was tweeting about everything, although I don't think I understood everything. But my senpai realized I was interested in Ruby from the conference. So a few years later, he suggested I attend Rails Girls Tokyo 2nd in 2013 to learn more about Rails and Ruby. And I thought it was cool. OK, I really liked Rails Girls, so I decided to start contributing to Rails Girls as a coach. And several years later, I decided to speak at RubyKaigi 2014 and submit a proposal about Rails Girls and diversity in tech, and it was accepted. So I spoke at RubyKaigi for the first time as a speaker, and they still keep this video and the website. So shout out to the RubyKaigi organizers for keeping all the historical archives. And this gave me more opportunities down the line. I got my second job with a referral from someone I met at RubyKaigi. He saw my tweets and thought I might be a good programmer, although I think it's a terrible and dangerous assumption today. But somehow it worked for me, and for us, hopefully. And when I interviewed for Google DevRel in 2017, I submitted the very video linked from there as an example of my English technical conference talk. And I think the hiring committee and interviewers liked the recording, and I got the offer. And also, the hiring manager also valued my Rails Girls contributions, because community contributions are also important factors of DevRel engineers. And it turns out Cloud DevRel at Google was one of the best places to calculate pi in the world. I always wanted to calculate pi, but I didn't have resources. I don't have a supercomputer sitting in my garage, fortunately. And Google Cloud DevRel had a tradition of Pi Day celebrations, doing some experiments with new cloud technologies. And so I had the right idea at the right place with necessary skills, like Linux and some like network optimizations and cloud. So I proposed the idea to my managers and directors, and they liked the idea. Well, I don't think they believed that it would be possible to break the world record, but they, anyway, let me try it. This is the DevRel website. So you see, like from 2015, you see 250 billion digits of pi, and then 500 billion digits all the way to 2018. But suddenly, in 2019, you get the world record. So that's a jump. And Greg Wilson was the director back then. So they all kind of enjoyed the idea, and it was a pleasure working with these people who are also Pi enthusiasts. And the rest is history. So I think this is a good RubyKaigi talk, but Ruby made the Pi world records possible, because without Ruby, I would have probably had a different career path. I might not work at Google, and I might not have broken the world records of Pi twice, because otherwise, how would I get the computing resources? And sadly, I'm not here talking to you all about the Pi world record and the story of the Rubyists who broke the world record twice. Thank you very much.